Good afternoon. I welcome back everyone for this technical session on CMSIS. CMSIS is a very widely used standards. Probably I'm not sure how many of the participants who are part of this webinar understands this or even aware of it. Probably you might have heard of the abbreviation CMSIS, I believe. So let's start with the presentation. And before I start with the presentation, I would like to request uh, to mute yourself because don't have that option of muting because I'm running WebEx through the browser, not from the app. So any questions, please put it in the chat window. I have dedicated time last 10 to 15 minutes to address your questions on this or any questions, even if it is out of the topic, even if it is not specific to CMSIS, anything on the software solutions which is offered by ARM. And I believe the team is might be working on the NTK software, microcontroller development kit software for ARM, or any questions related to ARM processor or ARM technology. Please feel free to put in the chat window. I shall come to it at the end of the session. So let's begin the session. Welcome you all once again. So I hope my screen is visible. Soumya? Right. So CMSIS, probably you might have seen this logo, the green CMSIS, the green block with the blue tick mark. So CMSIS stands for Cortex Microcontroller Software Interface Standard. So having been said that, in our agenda for today, and also as part of our email blast, what we did for the webinar attendees, for the webinar registration, I did include the information of that CMS has been extended to Cortex-A as well. So CMSIS was initially brought for Cortex-M devices, so Cortex microcontroller software. So specifically for Cortex-M devices, irrespective of the core, CM0, Cortex-M02, M33, M85, whatever is the latest step code now, all are CMSIS compliant. So we'll talk about what this standard CMSIS compliant means and how this will ease the life of the programmer or ease the life of the developer. So this CMSIS was also extended for some basic Cortex-A cores, basically Cortex-A7, Cortex-A9, Cortex-A8, like that. So all 32-bit lower end, I can tell Cortex-A cores, CMSIS is extended, but CMSIS is not, it doesn't support for higher Cortex-A devices which are 64-bit processor cores. Okay, so it supports in Cortex-M-based processor core with 32-bit core and Cortex-A. You can tell it as not lower end, I can tell preliminary Cortex-A processor cores which were designed by So this is the agenda. This webinar I'll be doing in 2 sessions. This month I'll be talking on CMSIS core, DSP, RTOS, and the next webinar, which will be in the next month, I'll be taking on CMSIS SPD, CMSIS PAC, CMSIS drivers, CMSIS DAC. Okay, because this is a very elaborative topic, I don't want to fill your brain with lot of information or sandwich your brain with lot of information. So let's give some time for the brain to digest this information, understand the information. So please pay attention. This will certainly help you for the end user who is into development of the software code based on Cortex-M, which will really going to help. And you may think, CMSIS, do I have to do anything specifically from my end? Absolutely no. If you are using a software which is CMSIS compliant, then everything is taken care by this CMSIS standard. Okay, but it is always good to know what is the CMSIS. Probably you might not be using the full feature of CMSIS which is provided by the ARM, or it was a standard actually in joint collaboration with ARM, silicon vendor, and the software tool vendor. Silicon vendor, I mean here, semiconductor vendor. So going forward in this session, I'll be using the word silicon vendor. So please relate it to semiconductor vendor. Software tool vendor can also be indicate. Thing itself, they give the software for ARM, or it can be IAR, or it can be open source tools like GNU. Okay. So I'll be software tool vendor means any vendor who is giving the software or compiler for developing the project based on Cortex. Okay. So these three CMSIS for DSP RTOS is what I'm planning to cover today for the first 40 minutes of the session. And later on, I'll quickly showing the Kyle MDK, just to give you an information where the CMSIS part is captured in Kyle. You should not feel okay, it is something it is being used in the background of the IDE or tools usage. No, it's part of your project itself. So I want to show you that so that you can appreciate the CMSIS standard what and all the three team came into collaboration and they came up with the CMSIS. So if not some things which you're not using earlier till now, maybe after this presentation we will start using it and try to explore more features of CMSIS. So CMSIS overview. This is just an introduction to show you what is, tell you few slides, 2 or 3 slides to show you what is CMSIS, where we can get the information about CMSIS. Okay, CMSIS has undergone a lot of changes now, with a lot of weather variations, weather configurations, weather flavors on CMSIS. So I shall be covering the basic one. Based on this, many other CMSIS configurations came into picture. So CMSIS helps the embedded industry in software standardization. So it basically provides an abstraction layer for Cortex and processor device. So what is abstraction layer? We shall be, like I can take it as a generic layer, which will be given by the standard. So we'll see what is that in the coming slides. And how is this going to benefit the developer?
So let's use yet another method. We're going to get to the last part.
Guys, please mute yourself. Thank you. And CMSIS, what is that for the embedded developer? Why at all ARM planned to come up with the CMSIS standard? Because it was in collaboration with ARM as well. And this idea was put forth by ARM itself. So why at all, why the ARM came up with the CMSIS? Well, it benefits the developer. Embedded developer is the final end user or a core team who sits and develops the software code for your project. Okay. Consistent software interfaces for silicon and middleware vendors. Software interfaces because, as I told, CMSIS was also brought in joint collaboration software tool vendors. Software interface. Suppose today I've written a code with Kyle MDK. Okay, and tomorrow you want to migrate this code to different software compiler, maybe IAR or a GCC, which is again CMSIS compliant, which is part of CMSIS standard. Then it will be easy for you to do this porting. It is easy to migrate it. So this is not only true between the vendors, tool vendors, it is also true between various silicon vendors and middleware vendors. Okay, or in the same silicon vendor, suppose if I take example of NXP. So NXP has various microcontrollers based on Cortex from M0 to M33, probably M23, M33. Or they may have the highest also, but they have the series based on various Cortex-M4 processor series. So suppose you developed the code with M0 processor core, you can easily port it to M3. M1 did not come for embedded, it went to FPGA. Okay, so suppose you have selected a device which is based on M0 code, microcontroller, you have developed a code in that, and in future you want to modify that project, and the team decides to update the device, maybe for a better optimization or better performing frequency, clock frequency, or maybe on the memory available on the device, all those. So the same project can be moved to the Cortex-M3 processor core because it is CMSIS compliant, and because M3 core is also backward compatible to M0. So M0 processors instructions are still best supported in M3. Even if it is up to peripheral level also, yes, it's possible because NXP has the same peripherals. Maybe from device to device, the set of peripherals change. So this is true even for the silicon as well. So it's exploit this simplified use across Cortex and processor-based device. So I gave the example of NXP. Suppose you want to move the project from NXP to SD device instead of reinventing the wheel and writing for scratch for SD device, you can directly move it. Processor core for SD still remains the same, but only the peripherals. Peripherals is the blocks which comes outside the processor core. What I mean is, hope the team is able to correlate. ARM does not give microcontroller of its own; it only gives the IP core. So silicon vendors like ST and NXP, they approach ARM, they license, they purchase this IP core at a higher cost. The core itself has inside some specific peripherals which will control the operation of the processor core. But onto this core, silicon vendor will put their own set of peripherals like timer, UART, I2C, USB, ADC, Ethernet. It can be SD card controller. It can be anything, any higher end peripheral. They can put it, and that they'll put that peripherals. They put it to the core, and they bring to the market as a microcontroller. Okay, so suppose the team is working on NXP, and then down the line you have to update the project, or you want to shift maybe because of the end of life of the specific device, because all the microcontrollers have the end of life, right? Those silicon vendors guarantee 10 years or 20 years of the shelf life or whatever. Sometimes it goes end of life abruptly. During COVID, like there was a high silicon shortage. So such cases, the team has to maybe move on with the chips which are available in the market immediately, whatever is available at your access for the cost or whatever. In such cases, you need not start the development of the project from the scratch. You can move the same project of NXP to SD. Only thing you have to concentrate on changing the code is specific to the peripherals, because NSD will have a certain set of peripherals, SD will have some set of peripherals, and the registers will be different. The registers which are used to access or configure those peripherals will be different, but the central processor core, Cortex-M3 or 4, will be still the same. So thereby the development time and the learning curve, everything will be reduced. So that was the advantage why CMSIS was brought into existence. So what is the CMSIS? Is they just use the ANSYS C and C++, and it supports all the data types which are defined in the standard int.h. Okay. So we will see more about this in the coming slides. So CMSIS structure. These are the various CMSIS main components. We have CMSIS core, driver, DAP, DSP, pack, RTOS, SVD. So what is core? As the name itself suggests, CMSIS core will give a set of APIs or functions which are used to configure, control the Cortex-M processor, and also to access the peripherals which are part of the core. Please don't confuse these peripherals with the peripherals which is included by the silicon vendor. When I mean core peripherals, these are the peripherals which are given as part of the Cortex-M core by the ARM itself. Okay, so this CMSIS core will give you access to the set of the functions through which you can access the core, control the core, and you can also control and configure the peripherals of the core. CMSIS driver. CMSIS driver is basically a driver for a generic driver for all the peripherals. Peripherals in the sense even for the peripherals put by the silicon vendor as well from the peripherals of the core. So it's a generic driver. Like suppose you are using a timer. So for timer configuration, what is the minimum skeleton of that driver? Generic driver is given that you have to adapt as per the device what you are using for your project. DAP is debug access port format specification. CMSIS DAP is Debug access port is the debug technology which was implemented in Cortex-M course. So to access that debug port, okay, for that also CMC standard was brought into picture. Then comes the DSP library. So this DSP, please don't think of this DSP if anyone of the webinar attendee, if you have earlier worked on DSP, exclusive DSP processor, TMS320 series from Texas, that DSP is different from this, though it's DSP. But here we have MAC unit, multiply and accumulate, and saturation instructions, and SIMD instructions, single instruction, multiple data. So these are the blocks which are present in Cortex M4 core, M33 core, and M7 core. Okay, all these processor cores has DSP block implemented. The course I'm talking is the one which are given by the So CMSIS package, device package. This is specifically given by the silicon vendor as part of the device family pack. So what all files they give, I'll talk about that in the next slides. CMSIS RTOS is a set of APIs so that any RTOS can define those APIs and user can use the whichever RTOS which suits the requirement. SPD is system your description file. This is basically to give you the access to all the peripherals of the particular device, which will help you to debug. At the time of debugging, you can see all the register names with the bits of those registers in JTAG, along with the JTAG debugger. So all this CMSIS related information is available on, if you go to arm.com and look for CMSIS, you'll get it. Or you can go to get the GitHub. From the GitHub also, you'll get all the CMSIS related information. So this I already told in the first slide itself. CMSIS was developed in close partnership with the key silicon vendors and the software vendors. So basically, this gives the ease to use and ease to learn programming interface for Cortex processor-based devices. The silicon vendors, you can see many things. Atmel, which is microchip now. We have Cypress, which is Infineon. We have Energy Micro, Freescale. We have Toshiba, Nuvoton. There are many actually. We have Giga. There are many Cortex-based devices now. So few are listed here. Then tool vendors, you can see here. Tool vendors is not only just software. Tool vendors is not just software, even it is a middleware as well. Header gives the middleware. Micrium, they give the RTOS. Prium is also an RTOS. So RTM is again the software for Cortex-M.
इन्सर्टचं चेंज नाही करत असेल तर तो तरी काय करणार आहे कंट्रोलर पासवर्ड मध्ये टाकून बघायचं
Please mute yourself, please.
किती यायचं आहे हे काय आहे आपलं व्होल्टेज 5 व्होल्ट आहे 4.999 पर्यंत आणून ते त्याचं पण चेक केलेलंच आहे उशीरच देतो तेवढा आता फक्त असं
Guys, please don't disturb others. Please mute yourself. No, I have muted everyone. Kindly understand. Thank you. So tool vendors is not just only the software tool vendors. Like middleware component will give its also software. Artos looking, it's also in software. These are some of the tool vendors it's listed. Now we'll come to the actual thing. What is CMSIS core? So as I told in the first slide, CMSIS core provides an hardware abstraction layer. So what is that HAL, hardware abstraction layer? That gives you the set of APIs for accessing all the core peripherals. So CMSIS, you have in M3 core or any Cortex-M core, all the peripherals like NVIC, which is nested vector interrupt controller, which is hardwired by ARM itself in the processor core, so that any level of nested interrupts can be handled by the processor core. This was not there in ARM 7, ARM 9 device. If any customer from this attendee is using on ARM 7, ARM 9, nested interrupts are not supported in that. You have to implement through the software, through your programming, to ensure that the registers are not corrupted and the processor can be brought back to the normal main flow. But in case of Cortex-M, NVIC was hardwired in the processor core itself, so that any any number of nested interrupt processing can be supported, and processor is capable of doing that. And we have APIs for feeding SysTick. SysTick is it's a timer, a 24-bit timer. It's a down counter. You can use it as a timer or even as a source which can generate the interrupt at regular intervals, usually as part of RTOS timer tick as well. System control block registers, these are all the registers associated with the excuse me, interrupts. We have MPU registers. MPU is memory protection unit, and though MPU is implementation specific, means ARM has given the option to include MPU, but silicon vendor will decide whether the MPU has to be included in that device. Similarly, floating point unit, FPU. So whichever device you see with the number start with F, like Cortex-M4F, this is processor code. Suppose if you go for STM32 F4 series, F means FPU. So hardware floating point unit is implemented in that particular device. So you may ask me, if FPU is not there, can I use Cortex-M string for floating point calculations? Yes. If you're using ARM compiler from KLMDK, in that matter, any compiler, they implement this floating point calculation through the library, through software library. And that computation time is more in comparison to the 100 floating point unit that everyone can understand. And with the context core, we can also give an API to get access to the intrinsic instructions. Means some instructions which you want to access directly in your C program, like NOP, everyone know NOP, no operation. In case of we have something called as wait for interrupt. Like for Cortex-M, suppose I want the processor to go to the sleep mode, and any interrupt can wake up the processor from the sleep mode. I'll directly use instruction in my C program, WF5. So wait for interrupt. Like that, we have barrier instructions. So there are many assembly instructions which you can easily access in your C program with the help of intrinsic functions. And all these intrinsic functions are defined as part of CMSIS code. So there is a misalignment. So now this you'll be able to correlate. This I'll show you now. You may see what these blocks I show you, but you'll be able to correlate when I show this in the Kyle ID, and you'll appreciate it. Probably you might not have noticed it also. You will notice it now. So CMSIS core, as I told, it's a set of APIs. And as I told, CMSIS was brought in collaboration with ARM, silicon vendor, and software tool vendor. Correct? So CMSIS core has to, as part of CMSIS core, silicon vendor has to give some set of files. Similarly, ARM has to give some set of files because ARM itself, ARM here I'm considering as a software tool vendor because ARM gives their license, MDK, and ARM Development Studio. They give their own ARM compiler. ARM has designed their own ARM compiler. Okay. So startup file, startup underscore device.s. Please note the naming convention. This is very much important. This naming convention will be true for any software tool or ID you're using, which are CMSIS compliant. Okay. So it's a startup underscore device.s. This is the startup code which is given by the silicon vendor. Okay. So this startup code will have the definition of the processor, stack and heap, and all the dummy exception table for the interrupt handlers. Interrupt handlers is all the handlers, all the interrupts which are generated by the peripherals outside the core. And it also has interrupt vector table, exception vector table we can tell, because in case of ARM, usually we interchange the word exception and interrupt. But in case of ARM, exceptions are the one which are generated inside the processor core, and interrupts are the one which are generated outside the processor core. So interrupt is something which is generated from the peripherals. Exceptions are something that are generated from the inside the core. Okay. So that exception vector table will be defined in the startup code. Dummy interrupt table for the peripheral interrupts, initialization of stack and heap. All these are done in the startup code. Then we have system configuration file. This is basically for setting up the clock for the processor and the various peripherals. We have system underscore device.h. This is the header file to access all the device specific or SFRs of the device. Because you know peripheral, how the programming can be done, it is only through registers. Theoretically, we know what each peripheral performs, but how we program it in the software, it is through registers. To access those registers, you need the device-specific header file. So this startup device.s, system underscore device.h. DC files are given by the silicon vendor. So in here, blue blocks are given by silicon vendors. Startup underscore device.s, system underscore device.c. Remember, startup code is always in the assembly. .s is the assembly file extension in ARM compiler. And device.h, device specific header file. So all these three are given by silicon vendor. Why? Because each silicon vendor, even in their own device, from one device to another, an XP for you from M3 to M4, or in M3 only they have LPC 1768 and 1788. So they will be changing the peripheral set of peripherals available in 1768 and 1788. So it's a set of peripherals change from device to device, and startup code should have the interrupt, dummy interrupt entry for all the peripherals, and device should also have all the registers defined for those peripherals. And device.c is specifically for configuring the clock for all the peripherals. So these blue blocks are given by silicon vendors strictly. Okay. So how when they license the IP core from the ARM, they'll get a template from the ARM. Using that template, they'll modify that template as per their device specific configuration, and they'll give all these blue blocks. Purple blocks are given by core underscore CPU. Here you will get all the instructions to access the CPU in the core. Core underscore CM instruction.h. This is specifically if you want to access any instruction in your C program in the form of intrinsic functions, those instructions are defined in the header file. CM functions, core peripheral functions. This is specifically to access the functionality of the core peripherals inside the processor core. And core underscore CM4 underscore CM70. This is specifically for CM4 because Cortex-M3 doesn't have DSP unit, whereas M4 has a DSP unit. It is implemented in the core itself, hardwired in the core itself. So SIMD is part of it, single instruction, multiple data. So you can see CMSIS core instruction access, which is given as part of core underscore CPU.h block. Purple blocks are given by ARM. So you can see whatever I said, knob, These are barrier instructions, wait for interrupt, wait for event. So all these are the some assembly instructions which will really be helpful if you get accessing the C function directly in your program. So you need not include this header file in your project. As soon as you create a project and create a C file, all these header files will be included by the ID itself. You need not add any of this explicitly. Okay. But these instructions are only part of the header file. So please open this header file and see these instructions are available and which you were not aware, and now you can use them. Barrier instructions, please refer to the on the on-site developer.com, though I did a session on barrier instruction on ISP, DSP, DLB. Probably I can find out the link, recorded link, and I can share it with you. These are very good barrier instructions, which will ensure that processor will execute in a normal flow. Okay. So next, CMSIS core, as I told, this is for the DSP. So DSP is implemented in M4, M7, and M33. So DSP instructions, it includes the multiply and accumulate, saturating instruction, and SIMD instruction. So SIMD means in a single instruction, processor tries to operate on multiple data. So this will various. This will be it like indirectly it's increasing the processor capability, but without any increase in the power consumption, because the time or the power taken by the processor to execute the instruction is same, but the same instruction is doing operation on multiple data. So when the operation is on multiple data simultaneously, performance increases automatically. The processing capability increases automatically. So SIMD features, some of them is a computation of 216-bit multiplication or 4 or 8-bit operands. All this can be done in a single instruction. Arithmetic, dual multiply, performance up to giga operations per second. So SIMD can also give you this much of performance, 3.2 giga operations per second for the processor operating at 800 megahertz. So all this information I've taken it from the outside. It's nothing I've exaggerated or written. Okay. So you have a good performance achieved with a nearly zero increase in the power consumption. This is again continuation of the SIMD instructions. You'll be getting the, I'll be uploading this webinar recording on the YouTube, and you'll get the link. And these instructions are given as part of a library. So you can access them in your C program. And now coming to special register access. This is for CM function.h given by ARM. So this is all the special function registers. All the control registers are part of the system control block, SCB block of the memory map of the Cortex-M. So these registers cannot be used right at the user mode. It needs a privileged mode or authorized access to write to this registers. Just you cannot in a C program you cannot access these functions. Okay, you can only do if you operate the processor in the supervisor mode. Cortex-M operates in two modes: privileged and unprivileged mode, or you can tell us threat or a handler mode. So privileged mode of operation, if you're making the processor to execute in that mode, it will execute. You can be able to modify or play with these functions. Basically, these functions as it will be used for configuring your own main Cortex-M core system. So this is for control register. Control register is only 2 bits only we use. Though it's a 32-bit register. One for setting to tell which stack processor use, process stack pointer or main stack pointer. So the scenario is if you're porting RTOS, the kernel scheduler will execute the code executed using main stack pointer, and the task or thread, whatever we write user, will be using process stack pointer. If your code is bare metal without any RTOS, then you can execute. You can make the processor to execute the entire code in privileged mode. That time you can access any of these registers. This is for interrupt status register. This is for setting the process state pointer, primary mask, fault mask, base prime. These are for setting the masks for the interrupts. So that to tell processor from which particular interrupt number the processor has to recognize and start executing. So all those registers. You have some registers specific to NVIC, NVIC nested vector interrupt controller, specifically to enable the IRQ, disable, enable the NVIC. So you may be seeing is what are these enumerations? These enumerations are nothing but it is having a number. If it is a negative number, means these exceptions are generated inside the processor core. If this enumeration is positive number, then it's the interrupt generated by the peripherals. So like that we have various functions. So you can say the ARMv6m, ARMv6m means some of the instructions or functions are not available for v6m. So to quickly tell you, v6m-based processor codes are Cortex-M0 and M0 plus. These both processors are v6m4. They are not v7m. Okay. Though it's a Cortex-M4. You might tell for Cortex-M there is no interrupt. Yes, we do have interrupt. NVIC is still there. But the number of interrupts supported there is very less. But if you go for, if I remember, it will be 32 or 8, but for Cortex-M3, we have to 256 interrupts. So processor can service up to 256 interrupts, but it is practically, we don't write so much interrupts for the application, but if such need comes, processor is capable of executing 256 interrupts. Okay. So CMSIS code system and configuration. We spoke about the startup underscore device.s, system underscore device.c. In CMSIS code slide, I told the specific C file is used to set the clock for the processor and the peripheral, various peripherals. So what does this C file has mean in system initialization? This will initialize the clock for the device, processor, or a microcontroller. And you have a global variable system core clock. So in between your application, if your core clock is updating for some reason, then this function has to be called. For example, I give you a scenario. Probably this may be for other device, but I don't have much exposure for the other architectures. NXP has PLL, phase lock loop. So initially the processor will execute from 12 megahertz crystal or whatever 16 megahertz crystal until the PLL clock gets stabilized. Once the PLL clock gets stabilized, that PLL output clock can be used as a CPU clock. That can be used as a system core clock. In such case, the system core clock update has to be called. And in case of NXP sample projects given by ARM, this is the first function or a first statement as part of the main function. I'm just giving an example. We can correlate this to your device, whatever you're using. This is cystic axis. So I told core also has a cystic timer. This is 24-bit down counter, and whatever value you load to it, like a ticks here, so it will count to 0 until generate an interrupt. Okay. So at what rate it generates an interrupt can be controlled by the value you are assigning to the ticks. In case of M3, M4, this is actually set to 10 milliseconds. So stick timer generates interrupt for every 10 milliseconds. So having said that, it doesn't, you should not be under the impression that this tick value cannot be changed. It can be changed. Okay. This can be done at the time of designing of the processor. Remember, it's not configuration of the processor. At the time of designing of the processor, silicon vendor will decide what is the tick value that can be assigned to it. So this can be used like a normal timer, okay, which we usually don't do because silicon vendors give set of timers, timer 0, 1, 2, 3, whatever is available for the application. But you still need a rational timer, you can use this. Usually this is used as a RTOS timer tick if you are implementing RTOS for Cortex-M. As I told, M operates in two different operating modes. So M is a act micro, it's a perfect processor for porting the RTOS application, for porting any microcontroller RTOS. So RTOS, heart of the RTOS is the timer tick. Means um, RTOS kernel works based on the timer intervals or based on the timer tick. Timer tick is once the ticks become 0 and once it reloads again that value, that is taken as one timer tick. So based on that, RTOS works. So sysdig config is the C function. It sets the reload register with the value tick and it loads to that register reload value. And it configures the sysdig, it enables the sysdig and it will generate to generate an exception as soon as the reload value becomes 0. When it counts to 0, it will generate an interrupt. So NVIC set priority, this is the function used for setting the priority for the sysdig exception. And this sysdig IRQ, this is the interrupt number assigned is -1. So minus I told, whenever enumeration negative means that's the exception is generated inside the processor core. And then it will enable the sysdig timer. The sysdig config function does all this. Okay. Next, coming to this also has a debug blocks. So in Cortex-M, from Cortex-M3 onwards, higher end, from Cortex-M3 and above, they have something called as trace feature. So there is a debug block instrumentation trace macro cell that can be clubbed with the serial wire viewer to get the trace capabilities of the microcontroller. So you can extract or collect the trace from the microcontroller with the help of these blocks, ITM. Okay. So what is ITM? For this also I have done a webinar already. ITM is instrumentation trace macro cell. To give a big view, why this was implemented by ARM is the traditional way of debugging till the date. User use the printf. So you should to see just to see that the program is in the correct flow, processor is in the correct flow of execution. But as an embedded developer, you should note that whenever you're using printf, you have to dedicate a UART because in embedded printf means it's sending the character string to the display. So for that, UART has to be initialized and that it has to be transmitted to the UART. But we cannot dedicate the UART. What these UART messages are sending, printf messages, it's just the debug messages. You can give it as like a heartbeat or something in between to see that the processor is in the flow. So for this purpose, just for debugging purpose, though from the final application code, which goes to your processor at the time of release, those printf will be removed. So this is just needed at the time of print for just the type of debugging. So to avoid the usage of the UART, ARM came up with the option of ITM channel, where instead of routing the serial output through the UART, it sends the serial output through the ITM, instrumentation trace macro cell. This is actually a block which has 32 registers, channel 0 to channel 31. Each channel has 32-bit register. Channel 0 is hardwired by ARM to send the printf style output. So whenever you use printf in your program and you're using the trace, if you have enabled the trace, for debug at the time of debugging, you can see the printf output routed through the ITM. So you can use the UART for your other application. Similarly, channel 31 is used for Cortex kernel and can be used for kernel awareness debugging. So if you're using KyleNDK and RTX RTOS kernel, if you develop the code, you have ported the RTOS kernel along with the application code to the board. Channel 31 can be used for sending the RTOS aware debugging information. So I told ITM is a block through which you can send the serial data or receive the serial data. So you need two functions here, item send character and item receive character. So you may be wondering, how will I define? So this is already defined by ARM as part of Cortex_CM function. You have to just call that function in your C program. Definition is taken care by the ARM. So ITM debugging support is available in the Microvision IDE. Right. So quickly, I'll show you in Kai. Yeah, I still 12 slides to go. So in the Kai, when you open the project, or even if you take RTE or older project, Microvision 4 project as well, you'll see startup underscore. Here, this is a project I've taken from NXP LPC 1768, which is Cortex-M3 core. This example project is given by ARM itself. And the startup, you can see startup underscore LPC 11xx.s. This was as part of CMSIS core NXP has to be. We can see here CMSIS Cortex-M3 core device startup file for NXP devices. So as I told, naming convention, you have to remember startup underscore device.c. Whatever is the device you are using, that specific startup code. This will be given by silicon only. Silicon vendor. Then system underscore device.c. This is specifically for initializing the clock. You can see in configuration itself. So this is clock for all the peripherals for USB, peripheral clock selection registers. Under this, you have NWDT, watchdog timer, timer 0, UR, type 2 CSPI. So this system underscore device dot c is specifically for initializing the clock for the processor. This is the system control, specifically for processor and all the peripherals. So you can see all this header files what I spoke about for underscore cm3.h. You go up, see. So you have cm function.h. You can see disable IRQ, enable IRQ, which I just explained you. This is all your intrinsic functions. You can see wait for interrupt, wait for event, send event. These are parallel instructions, ISP, DSP, DMP. So this core underscore C instructions, you can directly use now for any of these instructions in your C program directly. These are all already defined in this header file. This is the device specific header file. LPC17xx.h. I'll just show you. So this will have all the registers associated with this device peripherals you can see. Okay. Right. Let's go back to presentation quickly. So CMSIS DSP, this is given in the form of a library. Library is nothing but a set of APIs for all DSP-related information like vector operations, filter, Fourier transforms, or other DSP algorithms. Okay. We also have intrinsic functions for generating single instructions. So all these APIs are defined in ARM underscore math.h. So if in your project, if you have selected M4, M7, or M33 and are planning to use DSP, all these DSP libraries available in ARM underscore math.h. And this has been tested with Kyle as well as GCC and IAR. Well, it's the same thing even for this as well. And okay. This is all macros based on Cortex-M4. As I told, this BSP is there in M4. So for big Indian, little Indian, floating point, without floating point, like we have the CAMAT CM3 for library and Cortex-M4. CM3 for Cortex-M3, you may be telling, madam, we don't have DSP in CM3. Yeah, but other mathematical calculations you can still find there. Like that for big Indian, little Indian, floating point, without floating point, for all those various libraries are being provided by the. So coming to CMC Certus, CMC Certus is it actually it's a standard which provides the API for the software components which requires the RTOS functionality. So this allows the sharing of the components and reducing the learning difference, because see, wherever CMSIS word comes, it's basically it reduces the learning curve. Okay, so here you can see any third-party kernel, any RTOS kernel, they can implement this RTOS API, which are given, all these APIs given as part of CMSIS RTOS standard, and on that your application code can run. Okay, this way you can use any RTOS which is CMSIS compliant, and also this will be useful for even if this middleware vendor, and even offering the middleware stacks, if they're CMSIS RTOS specific, then also it will be easy for you to use it in your project. So RTOS API structure, the same blocks I had shown in CMSIS code, where startup underscore device.h, startup underscore device.c, device.h. All these three blue blocks are given by Silicon vendor. These pink blocks are given by the RTOS vendor. So whichever RTOS you're selecting, then it can be embossed from Sega, it can be infused RTOS from Freescale, it can be free RTOS, it can be micro OS RTOS, mucos RTOS from Micron. Whichever RTOS the user is using for their project, they have to give all these three files. RTOS lib is the definition of all the kernel APIs in the library format. Configuration to configure the RTOS, which timer it is using, at what time intervals it generates an interrupt, how many, what all kernel components is used, how many tasks you're using, semaphore, mutex, all those, message box, mailbox, all those, queue assignment, whatever kernel components, everything can be configured in RTOS configuration. CMSIS underscore OS.h, this basically it gives the definition of all the APIs which are provided as part of CMSIS RTOS standard. So this is a part of a generic RTOS. If you take an example of RTX RTOS, RTX RTOS is nothing but RTOS given by ARM itself. And Kyle MDK, Kyle CMSIS RTX RTOS was the first to become as part of CMSIS RTOS compliant. So whatever the APIs which are offered by the CMSIS RTOS, RTX implemented, that all the APIs were defined. So here, as per this previous slide I told, this underlying RTOS can be anything. Okay, only thing that RTOS vendor has to give these files given in the ping for the user to develop the code based on the RTOS. So the underlying RTOS can be changed. So because each RTOS varies from the performance, technical specification, switching time, or how well it is transparent with the project is defined with the interrupt, all those. What all kernel components it gives, what are all the APIs defined. So based on whichever the RTOS best fits the user requirements, the user can switch this kernel. But all this will remain still the same. The user has the freedom to choose the RTOS. So in case of RTX RTOS, RTX library, CMSIS RTX RTOS. On this you have CMSIS RTOS API. So this Kyle CMSIS, Kyle RTX RTOS has implemented these APIs which are given as part of CMSIS RTOS. And in the previous slide, I told the RTOS vendor has to give the configuration file. So in case of Kyle, RTX underscore conf underscore cm.c, this is the configuration file for configuring the RTOS kernel. And CMSIS underscore OS.h for accessing all the functions which are defined as part of CMSIS RTOS and over which our application code sits. So this RTX implementation is available under BST license, so it's available for free. So having said that, if you're developing a project using Kyle RTX RTOS, using Kyle software license, you want to port that to IAR, it is possible. Because this is CMSIS compliant and IAR is also CMSIS compliant. But this RTX RTOS project, whatever you're developing Kyle, can be still buildable by IR software. I'm just giving you an example. So this is for free, like RTOS kernel here offered by Kyle is available for free. It's given in the source code and you can use it for your project. So CMSIS RTOS quick reference. Sorry guys, I'll take maybe 5 more minutes. This is just this information you'll get it on site or even from the Kyle IDE on all the functions implemented for CMSIS RTOS. Okay. This particular slide is important because I just wanted to show tell you about the RTOS thread wait, the threads task status, ready, waiting, running, whatever. So CMSIS RTOS quick reference basically the start point of the RTOS kernel usually will be before main or after main. And usually in case of Kyle, it is we start the kernel by using the OS kernel start. In the main function after defining whatever is required, we will call the OS kernel start. This will actually start the execution from the task or thread which has the ID 1, whichever is created by the whatever we have created in our application. Okay. So here you have running inactive ready. Usually when it comes to inactive task, it will be an active task. It will define all the tasks in your threads which is required in your application code, and it will terminate itself and it will put itself in the inactive mode. Once it creates the task, before going into inactive mode, it will put into the ready state. So any task which is in the ready state is ready for the execution. So scheduler maintains the separate list for the tasks which are in the ready state, running state, waiting state, or inactive state. So once it enters the ready state, if the priority of the task is higher in comparison of the other task priority, it will be put to the running state. Okay. So this running state code task can also be preempted by the another task which is at the high priority, or if this task which is in the running state is waiting for an event. Once it waits for the event, it enters the waiting state. And once it gets the event, it will come back to the running state. If as soon as the task gets the event, if the priority of the task is higher, it will come to running state, or it will go back to again ready state for the execution. So kernel always executes the task which is at the higher priority. So these are just the various states which RTOS means in separate list in the queue, so that it will understand which task is the ready state, which is waiting, all this. So these are all the function definitions which I will be going into. I'll show you quickly the link where we get this information. We have for wait, we have delay. Delay engine is used by RTOS for allowing the other task to execute. One task is executing task 1. Task 1 can put itself in the delay mode and it will allow the other task, high priority task to execute. Or we can wait for an event with a wait. Event is nothing but a kind of flag. Event can also be waiting for a mutex or a semaphore or anything, or it is just an event flag. RTOS API implementation has 31 signal flags, but CMSIS RTOS supports 16 flags. Though there is no relevance for each flag, but you can define as required. You can assign each flag for a specific application. Say probably some data is available at the UART, it has to be processed by the processor to move the data to a memory or something. So one task will read the data from UART, another task will transfer the data to the memory. I'm just giving an example. So how will the second task will know that the data is available at the UART? UART will give us, that task will give a signal to this task saying that data is available, you are ready to now move that to the memory. So how they tell it? Through this synchronization, signal management. It just sets an event flag, and the second task, which is waiting for the data to arrive, will be polling for that event. Once that event flag is set, it will take the execution part. I mean, that is how RTOS works. So timer also, we have creation of timer, stopping the timer. and all this. This is for mutex, waiting for the tools can wait for the mutex. Once it's available, it will use and release. Similarly, we have binary semaphores. So this is for message and mailbox. So to quickly show you, I'll show you these definitions so that should not think madam quickly jumped it. It's available here. Uh, there are set of APIs. I'm just searching that. And or in the GitHub, you will get it. CMSIS. So if you see CMSIS here, you have core, driver, RTOS 2. Whatever I showed you was the RTOS 1 implementation. Later, RTOS 2 also came, which with advanced performance and the features included. Like, I'll just give an example, API reference. Like if you want to go for timer management, it shows all the functions associated with the timer. So all this information is available on site. Like if you go here, CMSIS core, CMSIS DM, CSP, CMSIS RTOS, it takes you directly to the site. So from there you get all this information. Okay. So that brings me to the end of the presentation. So next month I shall be probably doing this webinar of the second part on 21st or 22nd. You will get the email notification for the registration. So please do register. And do I have any questions? Okay, so there are no questions. So you can always send me to just put my email ID. If anyone could not follow any slide, this is my mail ID and this is my phone number. So please reach out to me. Send an email to geeta@gsmsdl.com and this is my number 9343756802. Any questions on this presentation or anything related to ARM you want to ask me, please reach out to me. I work here as a director of tools. I take care of sales and support both. Okay. So thank you once again for your time and I shall see you soon next month. Have a nice day.